because here like stars. Okay, so good afternoon. I wanted to say ladies and gentlemen, but ladies are not here today, except me. So anyway, welcome, and let me introduce Gabriele Sbaiz. So he did his study in the University of Trieste. Then his PhD, it's a little bit more interesting. It is not only Trieste, but also University of Lyon, because he was co-supervised. It was this thesis co-tutor between France and Italy. And his supervisor were from, let's say, French side. It was Francesco Fanelli, typical French guy. And from Italian side, it was Del Santo Daniele.
Yeah.
And today he will speak about one of his nice favorite topic about this fast rotation and inviscid limit for this SPG equation with general ill-prepared initial data. So please.
Thank you so much for the introduction, and thank you a lot for the invitation, of course. And yes, I would like to just briefly explain a bit the title of this talk. This is a joint work with a Brazilian collaborator, Leonardo Korsnov, and this was published some months ago. And the title is, let's say, a good recap of the results that we have presented in the paper, which are, first of all, we focus on the fast rotation limit, meaning that we describe the limit dynamics of our system when the parameter links to the rotation becomes singular, sorry. And the system is the surface quasi-geostrophic model that describes the dynamic of the temperature, the surface temperature in the ocean, for example. And the improvement with respect to the previous paper is linked to the general framework of the ill-prepared initial data. But we will see in detail in a while. Oh, not too much. Okay. Here you can see the equation, the surface quasi-geostrophic equation. Okay, I'm not so precise, meaning that usually the surface quasi-geostrophic equation is represented by the term involving the time derivative, and the divergence of theta, which is the temperature, and u, the velocity field, equal to 0. This is the standard SQG. Okay. Here, to be precise, this model is called the dissipative and dispersive surface quasi-geostrophic equation. Since you have, let's try to use pointer. Yeah. Since you have here the viscous term, where Ni is the viscous coefficient, and you have this term that is a sort of dispersive term. We will talk about it later. And for the two quantities, the two variables, theta and u, you have the link through the Ritz operator. Then the velocity field is linked to the temperature thanks to the Ritz operator in the following way. If you take u1, this is equal to minus r2 theta, and if you take u2, this is r1 theta. And if you compute the divergence of this vector field, this is 0. Okay, then your velocity field is a divergence-free vector field. Okay, here you have the initial datum. And now I would like to just explain a bit all the quantities in the previous equation. Okay, the domain is the torus times r. This due to technical reason in the computation. And I don't want to go in details about that. Okay, this is explained well in the paper. But I would like to stress the notation, meaning that I use capital lambda to indicate the fractional Laplacian operator, which is the square root of minor Laplacian. Okay, this notation is common in the SQG models. And I use this calligraphic R with index I to indicate there is transform where you take the derivative with respect to the xy coordinate and you take capital lambda to the power -1. This is an operator of order 1 and this is an operator of order 0 and the principal symbol of this one is minus, maybe I can write something. Yes, why not? The principal symbol is minus I, this is an I, sorry, Ci over the modulus of C. Okay, this is about the Richter. Okay, and we will play a bit with these two quantities since we would like to take the limit and we will see how for this quantity. And first of all, we fix nu, and then in the next step, we will take the combined limit for this quantity and this quantity also. Okay. Okay. Now I would like to describe from the physical point of view the previous equation and the appearing of the viscous term and dispersive term from the physical point of view. What about the viscous term? This is linked to the Ekman pumping mechanism. And as I said, N is the viscous coefficient and theta is the surface temperature. And instead, the term, which I called a dispersive term, is linked to the advection of large-scale buoyancy, which comes from the meridional variation of the Coriolis force. Okay, then this is, let's say, the counterpart of the Coriolis force that appears in Navier-Stokes. And indeed, this parameter measures the amplitude or the magnitude of the importance of this term. And it's the analog of the Rossby number, meaning that A is equal to 1 over the Rossby number, okay? Roughly speaking, the two-dimensional SQG equation are the counterpart of the 3D dimensional, Navier-Stokes equation. In this context, since you have the dispersive term, this is the counterpart of the Navier-Stokes Coriolis system in 2 dimensions. Okay, as I said before, as anticipated before, if we fix the Rossby number equal to a small parameter epsilon, we take as a parameter A 1 over epsilon. And for the moment, we fix the viscous coefficient. Okay, then we have these guys, which is the dispersive term, let's say the Coriolis force, which is singular when epsilon goes to 0. When epsilon goes to 0, this guy goes to plus infinity. Okay. Then we have a singular perturbation problem, depending on the small parameter epsilon. And we will see later, if we have time, that if we consider in addition also the inviscid limit, we take N, which is equal to a power of epsilon. Okay. Okay. The strategy to solve these kind of problems, which are the singular perturbation problem, is a standard matter now. There are a lot of papers concerning the singular perturbation problems. And the first step, for sure, is to develop an existence theory, which holds for any epsilon fixed. Then you fix epsilon and you check the existence of the solution. But then you have to perform some uniform bounds with respect to the epsilon parameter in order to extract the weak limit points of the sequence when epsilon goes to 0. And this is you can do thanks to Banach-Aloglu theorem, for example. And after that, then you have weak limit points. And you would like to characterize, at the end of the day, the limit dynamics of these weak limit points. but these weak limit points have to satisfy some constraint due to the structure of your system. And we will see how to find this constraint later. And okay, the last step is you would like to pass to the limit when epsilon goes to 0, and you would like to describe the limit dynamics of your system. Okay, the first paper concerning this type of model, meaning that the dissipative dispersive SQG problem, goes back to Kiselev and Nazarov in 2010, where they proved the existence of smooth solution in the torus, and also they state in the paper that the solution, the theory can be expanded also in R2 in the plane. And they tackle, if we indicate with this capital lambda and we put also this exponent alpha here, they prove the existence theory for alpha equal to 1/2. Okay, and this is called a critical exponent. And since they are able to prove for this critical exponent 1/2, they are also able to prove for the subcritical case, which is alpha greater than 1. Okay. This should be easy to extend when alpha is greater than 1/2. Then later, Cannon and Yang-Su in 2013, they are able to prove the existence of globally infinite energy weak solution for the supercritical case, meaning that they are able to fill the gap when alpha is less than 1/2. This is in 2013. Then the existence theory is already developed by other authors. And indeed, step 1 of the strategy is already proved in older paper. In the same paper, Cannon and Yang-Su, they prove also the limit dynamics of the system. But they use the strategy developed by Chemin, Desjardins, Grenier, and Gallagher and Grenier in their book, meaning that they truncate their system in coronas or in balls with two different radii. One goes to 0, one goes to plus infinity. In order to close the estimate, they need to use Stricker's type of dispersive estimate. But to do that, they need to construct in a very special way the initial data, meaning that the structure of initial data is prepared in a ad hoc way to close the estimate, meaning that they split the initial data into parts. One part, which is the one, let's say, without troubles, is in L2, and the other part of the solution, which is the problematic one linked to the oscillation and to of the system, they need more regularity to close the estimate. Then they need h to the power 2 minus alpha. This is in order to close the estimate. Then they need smooth, let's say, smooth solution, or better, smooth initial data to close the estimate. And more recently, in 2019, Kozlov, Nika, and Planas, they prove the limit dynamics for the whole range of alpha between 0 and 1 using the relative energy inequality. And in that paper, they need to ask to use well-prepared initial data, meaning that they ask that the initial data converges strongly to the target data. And this is something that can be extended, of course, to the ill-prepared data, meaning that we do not require any kind of structure of the initial data as they did Canone, Miao, and Su, and we don't need any strong, a priori strong convergence of the initial data. Yes, this is, of course, in that paper they use only well-prepared initial data. Indeed, in our theorem, we need just to ask uniform boundness of the initial data in L2. This is enough. Meaning that it's enough to have L2 boundedness uniformly, okay, with respect to epsilon in order to extract weak limit points for the initial data. And then we are able to prove that for any time, since we have the existence theorem that tell us we have global in time weak, finite energy weak solution, when epsilon goes to 0, we are able to converge weakly star in the red space, which is an infinity in time L2, that is the energy space, and intersection with L2 in time H1 dot, where the dot for me is the homogeneous of the space in order to control the viscous term. Okay. And also you have the constraint for the temperature at the limit, which is the following one. The derivative with respect to the x1 coordinate, which is equal to 0. And the target temperature, theta bar, is a weak solution of the following linear equation, which has a parabolic structure. That is a derivative in time of the temperature plus the viscous term, but just considering the second coordinate. Indeed, this capital lambda 2 is just the square root of minus the derivative with respect to the second component. Okay, this is the main theorem and the limit of the limit dynamics of your system. Okay. Okay. As I said, the existence theory was already developed by other authors. Then it is okay for us. Then for any epsilon fix, we have the existence of the solution to the original system. But now you have to find some uniform bounds, and the uniform bounds come from the energy inequality. The energy inequality is just a multiplication by theta in the L2 space, and of course you have the contribution of the temperature in L2 the power 2. You have the viscous term here. You don't have the Ritz operator since it is antisymmetric, then in L2 vanishes, and this is bounded by the initial data. If you remember, in the hypothesis of the theorem, the initial data is uniformly bounded with respect to epsilon, then this is less or equal than a constant, and then you can extract, thanks to Banach-Aloglu, weak limit points for the temperature, but also for the velocity field, since they are linked through an operator of order 0. Okay. Till now, we have the existence theory already performed by other authors. We have found uniform bounds, then we were able to extract weak limit points. Now we would like to characterize the limit points of this sequence. And to do so, we take the momentum equation and we multiply by epsilon, everything. Then we have here epsilon that multiplies the the term concerning the derivative in time, the convective term, and the viscous term. All these quantities are uniformly bounded thanks to the energy inequality. Then it is multiplied by epsilon. When epsilon goes to 0, this guy goes to 0. Also, this guy is uniformly bound, is the initial datum, and then it is multiplied by epsilon and goes to 0 when epsilon goes to 0. Then you have just this guy, and you know that theta epsilon converges to theta bar. Then here you are. You have that in the sense of the distribution, R1 theta bar is equal to 0. Okay, now you need to compute the Fourier transform you pass in Fourier, then you check that you can avoid direct deltas, and if you are able to avoid direct deltas, you come back thanks to the anti-transform of Fourier, and you are able to state that also the one of theta bar is equal to 0. Okay, this is just a matter of computation. Okay. Then, roughly speaking, you are able to pass in the limit for the term concerning the derivative in time, for the term concerning the viscosity, since you have uniform bounds and energy estimate for the viscous term, you are able to pass in the Coriolis term since it is an one-order operator, and that's it. The only term that you are not able to pass directly to the limit is the term which is the convex term. You have a product of function, both are converging weakly, then you cannot state the convergence of the product, then you need to find some strong convergence, one of the two quantities. Okay. And then you use the structure of the system, meaning that you take this function in such a way, then you can rewrite the convex term thanks to the structure of the test function, then the one of phi is 0, then you have just the 2 of phi, and then you can take the second component of the velocity field. And since you are playing with the torus cross R, if you take the average, you end up here. Okay. Now you have these guys here. And you would like to understand the dynamic, the limit dynamic of this product. And to do so, you have to split this guy into terms. One, which is the multiplication of the averages, and the other one, which is the multiplication of this oscillation. Since you can write every function as the sum of average or means plus oscillation. And of course, all the cross terms are 0, meaning that if you have average multiplied by oscillation, this is 0, you can compute explicitly. Okay. Then now the goal is to analyze the convergence of this guy and the convergence of this second term. The goal is to prove that this guy converges to what that you need, and this goes to 0. The oscillations goes to 0. Okay, then first step, we analyze the means, the averages. First of all, you notice that due to the property of the list operator that you are playing in the torus, then if you take the average of the list operator, this is 0 in average. And then you have just the derivative in time of the average of the temperature equal to an external force. Okay, it doesn't matter what is on the right hand side. And what about the external force? The external force is uniformly bounded. You have just to find the right space where this external force is uniformly bounded. Okay, this guy is in L2H1 half, then is in H1 half, then more or less, roughly speaking, if you take a derivative, this is in H minus 1 half. What about this term? Okay, this term is a bit not so easy, let's say, to control directly. We used the paradifferential calculus, meaning that if you use the paradifferential calculus, you are able to bound this term in the Bezos space, which is B, which is this one, B minus 1 half to 1. Okay, this is the right Bezos space of such a quantity. The space is embedded in H minus 1 half. And since you are taking one derivative more here, you have the divergence operator. This is in H to the power minus 3 half. Okay. Then all the stuff is uniformly bounded in L2 in time, H to the power minus 3 half. If you're looking, of course, the derivative in time. And then that means that the temperature, the average of the temperature is uniformly bounded in W12 for the time and h minus PR for the space. You already know the uniform bounds for theta, and then you play a bit gaining and losing regularity in time and space with Gaussian, and you can say that this quantity, the average of theta, converges strongly in, for example, L2 in time and L2 in space. Of course, this is not at all the optimal space that you can reach, but it's enough for us to pass to the limit. Then it's fair to take L2 in time, L2 lock in space. Then you have strongly convergence of these guys in the previous space. You have weakly convergence of the second guy, then you have the convergence for the product in the sense of distribution. That's it. Okay. Now, if you remember, we have split the term in mean and oscillations. Okay. Now we already control the means, and then we have to control the oscillations. To control the oscillation, we use the system. And this is why we are able to extend the previous results. The strategy that we employed is called compensated compactness, meaning that we use the algebra of the system in order to find spatial relation and spatial cancellation to pass to the limit, in order to find compactness that help you to push the original system to the limit. Okay. The compensated compactness is first developed by Lyons and Masmidi in 1998, yes, with a first paper concerning barotropic Navier-Stokes, and later adapted by Gallagher and Saint-Raymond in 2006. Well, these are just the two main papers concerning this strategy, and then, of course, was improved and developed more. And in this way, thanks to this strategy, we are able to take the e-prepare initial data. We paid something which is the rate of convergence. Thanks to this strategy, or due to this strategy, we are not able anymore to have the rate of convergence of your original system to the target system. You just know the convergence. Okay, then you take your system, you multiply by epsilon, and you have on the left-hand side the epsilon, the derivative in time of the temperature, and the dispersive term. And then on the right-hand side, you have epsilon and an external force, doesn't matter. The external force is the one of before, that is uniform bounding in some spaces. And thanks to the link between the temperature and the velocity, you know that this guy is the second component of the velocity. Okay. Then you can rewrite all the system taking care about the oscillation in this way. You have epsilon, the derivative in time of the temperature, and you have the oscillation of the second component of velocity, equal to epsilon and an external force. Okay. Now, in order to pass the limit, we have to play with the system. In order to play with the system, we need to play with smooth quantity in space. In order to smooth quantities, smooth quantities, we apply, this is the little poly cutoff, but you can think about it like a mollifier. Then you mollify your solution in space, not in time. Then still you have troubles in understanding the limit for the oscillation in time of your solution. You don't have compactness in time for your solution. Okay, then now, thanks to this proposition that tell us that the regular solution, or better, the regularized solution are close to the original one, roughly speaking, you can play with the approximate equation, where your quantities are all smooth in space. Then you can take derivatives, you can take everything. Yes, the proof of the approximation solution are close to the original one is the following. You start by regularizing the first quantity, then you have the identity minus the mollifier, let's say. This mollifier goes, or like you have a decay of the modifier of 2 to the power minus m. Then when m is going to plus infinity, this goes to 0. Then this term, the second term, goes to 0. And similarly, now you regularize also the second quantity, which is the velocity, and still you have the identity minus the modifier, and then also this term goes to 0. Then we have proved that you can play with the regularized solution instead of the original one. Okay, I recall again this system that we have seen before, just to have in mind it. Then now you can multiply everything by theta. And here you have theta, u, epsilon, and then on the right-hand side you have these guys multiplied by theta, and you have the derivative in time. Then of course you can write it like here, 1/2 the total derivative in time of theta squared. Of course, all these quantities are uniformly bounded, multiplied by epsilon goes to 0. Then roughly speaking, the oscillation are going to 0. Last step of the analysis is to characterize the limit dynamics. You would like to pass term by term at the limit. Okay, to pass here, no troubles, no problem. You can pass through thanks to the energy inequality. Now, up to now, we have analyzed also this convective term. Then you are able to pass also in this term and also in the viscous term. And the initial data is okay. The convective term, you have the convergence that we have seen before, meaning that you have the convergence just to the means, since the oscillations are going to 0. But now the system plays a crucial role, meaning that since you have this relation between the second component of velocity field and the temperature, this guy is 0. Okay, because you can put R1, you can put R1 on the test function, the test function, R1 test function is 0, then this guy is 0. Then at the end of the day, the limit dynamics is the linear equation with parabolic structure that we have seen in the main theorem. Okay, it's here. Of course, you have to think everything, sorry, the joke. You have to think in the sense of distribution. Okay. Okay, and this is the fast rotation mean limit when you keep fixed the viscosity. What happens if you are also considering the vanishing viscosity limit? Here, to consider the vanishing viscosity limit, we need a regular solution in Nečas with s greater than 2, meaning that we need the embed in W1 infinity, since we would like to propagate the regularity of the solution. And this, we will see why, but no, we will see in the next slide. It's better with the computation. And then if we have that initial datum is in this space, which is regular, and you take the vanishing viscosity limit, then you are able to find existing time T star, which is uniformly bounded with respect to epsilon, such that you have the convergence of the temperature to the target temperature in, of course, this space, the regular space. And here the limit dynamics is trivial, since you are losing also the contribution of the viscous term. We have just preservation of the initial datum along the motion. This is a super trivial limit dynamics. Okay, this is the trouble that I described before. If you compute the L2 energy estimate, you have still the L2 in time, L2 norm of the temperature and the viscous term, but here in front of the viscous term, you don't have the Ni fixed, but you have epsilon to the power beta. And when epsilon goes to 0, you don't have any control on the viscous term. You lose a lot of regularity. In order to propagate the regularity of the solution, then we need a regular solution. Indeed, we need higher order estimate. how to compute. You apply the building blocks of the little quality theory, and this is okay, the term involving the time derivative. Here you have the convective term. Since you would like to put the other block here on the temperature, you have to pay with a commutator here. Okay. Here, oh, sorry, the third term is the viscous term, and the last term here on the left-hand side is the dispersive term. Okay, the dispersive term still is an antisymmetric operator. Then, if you compute on L2 estimate, this is 0. This is 0 because you put the gradient. You can put the gradient on the velocity field, and the field is a divergence-free vector field, and also this guy is 0. Then you have an Nečas estimate for the temperature plus the term involving the which is the viscous term, roughly speaking, in the following space, and you have the initial data plus this is the contribution coming from the commutator. And this is now it's a standard matter. You would like to find a time for the existence of the solution. Then you have to ask a time, you have to find a time such that this is controlled. Okay, this is the goal. You would like to find a time to start where the solution are uniformly bounded with respect to our parameter epsilon. Then you start by defining time depending on epsilon, which is the following. You require that this quantity is bounded by the initial datum, for example, by a constant, doesn't matter. Then this is a standard matter in the existence theory or the existence time theory. You have that the time is bounded from below by a constant and the initial data. Since the initial data now is uniformly bounded by hypothesis, you are, this is a bit, doesn't matter, it's hidden. You are able to find a time which is independent on epsilon. And this time, which is the supremum of all the previous time, is strictly greater than 0. This is important. Otherwise, your time of existence is going to 0 with epsilon goes to 0, and then you are proving nothing. You have no existence of solution. Okay. And it's important that your initial data is uniformly bounded, then you are able to find a time of existence of solution which is different from 0. And now the convergence. Now the convergence is easier, I would like to say easier with respect to the previous one, since the dissipative term now converges to 0. Since this guy is uniformly bounded in a regular space, but this is also multiplied by epsilon to the power beta. And when epsilon goes to 0, this guy goes to 0. And then the limit dynamics in the sense of distribution is the following that we have seen before, is just the derivative in time of the target temperature. Then we are just preserving the initial datum along the function. Okay. Okay. Now, I would like to discuss about some work in progress. Our work in progress is, I would like to start from the second one, let's say. We are developing an asymptotic analysis theory for a model which comes from the collective behavior, which is the Hooker's-Mail model that describes the interaction of agents. And this is a bit tricky, meaning that usually in this community of collective dynamics equation, the limit dynamics is every time characterized thanks to relative energy inequalities. Now we are trying to use the compensated compactness in order to extend the previous theory, but I would like that it's not enough, and then you have to try to find a good balance between this compensated compactness technique and the energy inequality in order that they, let's say, talk together and in order to close the estimate. And okay, this is, I would like to say, this is a model are important also, for example, in the economics description of models, since recently I discovered that this model characterize the market fluctuation. And I don't know, we will see how this work can go on. And the second one that I left for the final consideration is the asymptotic analysis beyond critical regimes. Then I will try to explain better. This is a work with Matteo, which is here. Then there we are trying to describe the limit dynamics for particular regimes that are not covered in previous paper, which are in the middle between a regime which is called critical, where the fluid number, which is a number linked to the stratification, is equal to the square root of the MAC, which is another number linked to the pressure. Then we have a sort of link between the stratification effect and the compressibility effect. And now we are trying to push just beyond these critical regimes, meaning that we would like to go beyond this critical scanning, and we are working on it. But of course, we are still not able to cover the strong stratification regime. This is out for the moment. And this is very interesting, since we are trying to reach this important strong stratification regime, but still we are not able. I think, yes, this is ICE. This is some references in the talk. The first one was, okay, it's in alphabetical order. The first one is the one by Cannone, Miao, and Su, where they discuss both the existence theory for global in time weak finite energy weak solution, and also they prove the limit dynamics with Picard estimates. The second one was the first previous paper concerning our model in 2010 by Kislev and Nazarov, where they prove global regularity in the torus in T2 for the solution in T2. This is another improvement thanks to the relative energy, relative entropy inequalities, but still with well-prepared initial data in 2019. And the last one, which is our paper that I try to explain you today, is the following, which appear this year, and the one was the main topic of this talk. I think I can stop here, and I thank you so much for your attention and for being here. Thank you so much.
Thank you very much, Gabriele. So,